It is 2 o'clock, and I believe the meeting is now recording. So let's hope that there's no issues with that so that I can post this later on. So before I begin, could I get one person to confirm for me that they can hear me?
We can hear you.
Very good. Okay, I've not used Teams very often lately, so I don't want this to be a total disaster. So thank you for clarifying. And then the next thing to confirm is once I get over to it, are you able to see the screen that I'm sharing?
Yes, we can see.
Okay, perfect. All right, so we'll get right into it. It's going to be obviously some differences between this and a normal review session. They will, for the rest of the semester, be in person. What I'll ask is if you have questions, I'm going to ideally save them to the end of each problem, in part because a lot of times you'll have a question pop in your head that I will then answer as I go through the rest of the problem. So that'll save us some redundant questions. And then also just easier for me to monitor on Teams if I'm going, just back and forth once every question. You can shout them out. That's in some ways preferred because then I don't have to look for you to, raise your hand or look in the, typed messages. But at the same time, if you want to, if you'd rather just raise your hand or type it in, I'll try to catch all of those questions as well. Maybe I'll get a little bit behind on those, but I'll try to keep up with it. So however you choose to ask questions is fine, and whenever you choose to do it, or whatever you choose to ask about. So you can ask about the specific problem that I go over, and you're also welcome to ask questions about anything that you think is related to that topic that you want some clarification on. So it's pretty open-ended, and obviously this is for your benefit primarily, so whatever we discuss today is totally fine with me. All right, so if there's no procedural questions that you have, get the habit of checking regularly. So it looks like we're good. And I will get right into the first problem. So this goes back to the very beginning of the course on mass laws. So we're asking you to identify in this problem which mass law is demonstrated by the fact that sodium chloride mined in Goderich, Ontario, which has the largest salt mine in the world, and sodium chloride mined in Kura, Pakistan, which is the second largest salt mine, both consist of 39.3% sodium by mass. So for these types of problems, we're looking at a situation that's presented to us. And so what we can do is, we'll go through the answer choices and kind of give a brief description of what each of these mass laws means, and then try to relate that to the situation that we're given here. So choice A, which is law of conservation of mass, that's probably the most straightforward one. That tells us that matter is neither created nor destroyed during a chemical reaction. And in this problem here, we're not talking about a chemical reaction. So this does not seem relevant to the situation we're presented. We're talking about mass percents of elements, but we're not talking about a chemical reaction converting one substance to another. So that we can probably eliminate that one. For B, which is definite composition, B and C are the two that we kind of most often mix up of these three mass laws. And so the first one, which is definite composition, or sometimes called definite proportion, you might see it that way on your exam, but either way, it'll have the word definite in it. So that's going to be talking about the elemental mass percentage of a single compound. And so this is saying that, any substance, typically a compound, but it also applies to elements themselves, which are 100% of a single element. But any substance has specific mass ratios of elements. All right, now this one sounds like what we're describing here because we're talking about a substance, sodium chloride, and we're told that it has 39.3% sodium by mass. Now we do want to make sure though that we can distinguish this one from multiple proportions, which is the one that's going to be closely related and sometimes a little bit confused with definite composition. So the key distinction is that if we're talking about law of multiple proportions, we're talking about relationships involving two or more different substances. So I'm not going to write out the whole law of multiple proportions because it's kind of wordy, but when you're trying to identify it in a question like this, multiple proportions requires that you're talking about two or more different substances, first of all, and they have to be formed from the same elements. So in this problem here, we're only talking about a single substance, sodium chloride. So it's not multiple substances, it's one single substance, sodium chloride, from different sources, but not different substances. So the one that's going to work best for this one will be choice B. Now, if we go through, we should also eliminate choice D. I haven't done that yet. Dalton's law, we'll learn about this later in the semester. This is not actually a mass law. Not to be confused with Dalton's atomic theory, which is a theory that explains the mass laws, but Dalton's law, which is a separate law dealing with gases, is not something that we're going to talk about until much later. So the one that fits best is choice B because we're dealing with the composition of a single substance, which would not depend on the source of that substance. All right, so does anybody have questions on that problem or on the topics in general related to mass laws? Okay, so we are silent, so I will move on to the next one and keep us going. Be mindful of our time. Okay, so the next question here deals with atomic structure, the subatomic particles that are present in atoms and ions. And it wants to know how many neutrons and electrons are present in a 55 manganese plus 3 ion. Okay, so the first thing to decompose is what's going to be the anatomy of this atomic symbol. So we gave you an atomic symbol here that has a symbol and two numbers attached to it. So let's talk about what those exactly mean. So this is 55 Mn3 plus. So when it's written in this way, what we have to recall is that the number that's on the top left, if it's given to us, that's going to be the mass number. And that's going to tell us the number of protons plus the number of neutrons. Basically the sum of the subatomic particles that are in the nucleus. Okay, so that's what the mass number tells us. And then this number up here, which won't always be there, but this, if it's given, is going to indicate the charge, telling us that this is actually an ion, not a neutral atom. Okay, so that's going to be the two pieces of this that are critical. Now, what we're going to typically start with for problems like this is identifying the number of protons first. And the reason that that one is usually the most straightforward to get is because it comes directly from the atomic number. Now, in this atomic symbol here, we didn't give you the atomic number, but that's going to be directly related to the symbol, the element, which is Mn. So to find the atomic number Z, which would go down here if it was given, but it's not given to us in this problem, it would go on the sort of bottom left of the symbol. Then we have to go to the periodic table to identify that element. So I'll flip over to the periodic table here, which you should still be able to see. It's in the same shared window, I believe. And we're going to find Mn. So this is one of the first 36, so you should be familiar that this is called manganese, and it's right here, middle of the 3D block. Okay, so but the key part of this, which I'll try to zoom in on a little bit, in case that's small for you guys, is that manganese is right here. The number above that is the number 25. Okay, so that's going to tell us the atomic number of that element. All right, so when we go back to over here, we know because it's Mn and the atomic number on the periodic table is 25, that's going to be the number of protons in the nucleus. Now, we're not actually asked for that number here, but we need it to get the other two. So now that we have the number of protons and we know that the mass number is 55, 55 is equal to the number of protons. So this is going to be the mass number, which is sometimes given as A, plus the number of neutrons. And then with a little bit of algebra, we can find out that the number of neutrons, abbreviated as N0, is 55 minus 25, which is 30. So we get the number of neutrons by difference. So we can eliminate already 3 of the answer choices because they have the wrong number of neutrons if we trusted ourselves to do that. All right, and then finally for the number of electrons, that is going to relate to the charge. So if this was a neutral atom, the number of protons, the number of electrons would have to be equal. They would both be 25. But we're telling you that there's a 3 plus charge here. So the 3 plus charge comes about because we have 3 fewer electrons than protons. So we have 25 protons, but there's going to be 3 fewer than that for the number of electrons because of the plus 3 charge. So that's why we're going to subtract 3 from this, and we're going to leave us with 22 as a number of electrons. So 30 for neutrons, 22 for electrons, and that's going to be choice B here. Okay, so the number of neutrons requires us to have the mass number and the atomic number, and the number of electrons requires us to consider any charge that might be present, which in this case there was one. All right, so that's again subatomic particles, and knowing all those ways of finding the different numbers of protons, neutrons, electrons for both atoms and ions are all going to be fair game for you guys. So do we have any questions on that problem or that topic? All right, you guys are easy so far, but please feel free to chime in with any questions you have at any point. All right, on number 3. All right, so as you can kind of tell from the format of this exam, and if you're keeping track of sort of where we are in the textbook, those were really the only 2 questions that dealt with chapter 1. So we're already now on to chapter 2, which starts with electromagnetic radiation. All right, and so this problem here, we have an infrared photon has a wavelength of 1,234 nanometers. What are the energy and frequency of the photon? So this problem sort of deals with both relationships that we would have involving photons and their wavelengths and frequencies and energies. So there are 2 different equations, and you need to know in a specific problem which one to use. In this case, I'm using them both just to sort of show them both to you. In reality, most of the exam questions would require you to use one or the other, but not necessarily both at the same time. But nonetheless, what those are is the first one we talked about, which is just dealing with the wavelength and frequency relationship, is that the product of those 2, nu, which is the frequency, lambda, which is the wavelength, equals speed of light, c. And that's going to be a constant on your periodic table, so you don't need to memorize that number, even though you'll use it a lot. And then the other relationship is for the energy of a photon. So the energy is equal to a different constant, h, Planck's constant, multiplied by nu, which is again the frequency. And then we can combine these 2 equations because lambda is equal to nu is equal to c divided by lambda. And so by combining those 2, we get an alternative form, hc over lambda. So there's really 2 equations, and then a third one that emerges by combining those 2 algebraically. And in this problem here, we're going to end up using both of them. And so the first thing we want is, well, we can do it in either order, but we want the energy and the frequency. So whichever one you choose to do first, but energy is listed first, so let's do that. We're going to use this form of the equation here. Energy equals hc over lambda because wavelength lambda is what we're given in this problem, 1234 nanometers. Okay, so that's what we're going to use first, or if that's how you choose to do it, that's totally fine. So we're going to go hc over lambda. And again, to remind you, h and c are both fundamental physical constants, and they're on your periodic table. So again, look at the bottom here. This is the exact same periodic table you'll have on the exam. H is here, 6.626 times 10 to the minus 34. C is the last one, 3 times 10 to the 8th. So those are those 2 constants that we used a lot in chapter 2 problems, and we're going to use both of them in this equation. So H, which is 6.626 times 10 to the minus 34, and the units for that are joules seconds. And then C is the speed of light in meters per second. Now, the one thing we have to be careful about when using both of these equations is that we have the correct units, especially for lambda. So in this, we need SI units. All these constants are in terms of SI units, and particularly, we see that the speed of light is meters per second. So that means our wavelength, which is a measure of distance or length, has to be given to us in meters, or we have to use it in meters to be able to put it in the equation. So that's the one unit conversion we'll have to do in this problem, which is that the wavelength in meters, we're starting with 1234 nanometers, and then nano is 10 to the 9th, so there's, or 10 to the minus 9 technically, but there's 2 ways of writing that, but it's going to be 1 meter is 10 to the 9th nanometers, if you prefer positive exponents, or alternatively 10 to the minus 9 meters over 1 nanometer works fine as well. Mathematically, they're the same. So when we multiply that out, we get 1.234 times 10 to the minus 6 meters. And so that's the number we're going to put in here for lambda in the correct units, 1.234 times 10 to the minus 6. And then so when we multiply that across, we get 1.61 times 10 to the minus 19 joules. So that's the number we get for energy. So that's going to match choices A and B. So again, if we trust ourselves for the first part, by elimination, we can get rid of C and D. And then finally, we have to calculate the frequency as well. And so for that, we're going to use this first equation here and solve for nu, which is the frequency, which is just c divided by lambda. And so that's going to be speed of light is the only constant in this equation, 3 times 10 to the 8th, divided by the same wavelength, still in meters, to make sure the units match up. And when we divide those two, we get 2.43 times 10 to the 14. And the units for that, it's inverse seconds, but more commonly written as hertz, Hz. All right, so that's nu, and then that's our energy up there. And so the answer choice that has both of those would be A. Now, in problems, in the exam, we have a lot of problems like this where you have to calculate numbers. And, given the timing of the exam, you have 75 minutes to do 20 questions. You're looking at, 3.75 minutes per question. You're not going to probably have time to do every problem, multiple times. You're going to have to, move through and be efficient to make sure that time's not an issue. For most people, time is not an issue, I should say, but trying to do the exam twice in a lot of time might be a challenge. So what's helpful in numerical problems like this, especially if you don't have time to completely check your work and recalculate everything, is to make sure at least the order of magnitude for the answer is reasonable. And so, what's nice to remember is that if we're calculating the energy of a photon and we're in, somewhere in the typical region of the spectrum that's, UV to visible to maybe infrared is where we're going to most often be looking at in the context of chemistry, your photon energy should be somewhere on the order of, 10 to the minus 18, 10 to the minus 19, somewhere in that negative exponential range. So if you calculate an energy that's, a huge number like positive exponent or way, way smaller than this like C and D, or then you probably made a math mistake. And then similarly with frequency, typical frequencies for electromagnetic radiation in the parts of the spectrum we work with are, around gigahertz range, 10 to the 14th, 10 to the 15th hertz or so. And so that's going to, or terahertz even, but anyway, it's going to be typically a large positive exponent on that order. And again, if you get a negative exponent for frequency, that's almost certainly a math mistake that you made. So like choices B and D here have really small numbers for the frequency. That's not a number you'd expect to get for anything that we're going to calculate. So that might cue you in that you messed it up if you got one of those. Because a lot of times, if you have a multiple choice question that's numerical, some of the answer choices are going to be common mistakes that people make. So they're ones that they're not just random numbers. They're ones that you would be likely to pick if you made one of the more common mistakes that comes up. A lot of the numerical questions, you actually have to type your answer in which case you can't really eliminate answer choices like we did here. But still knowing approximately the appropriate order of magnitude for a typical number that you would calculate in a problem like this can help you easily identify if you made an obvious mistake. All right, so that's just a little bit of word of advice on some of the numerical things. So do we have any questions on that? So there's someone in the chat sent something, so let me check what it says. Will the test do the will the test do the calculation using the exact C value or round it to 3 times 10 to the 8th? It doesn't matter. So you are right that the value of C is given to us on the periodic table with like, I don't know, it's like 5 digits, at least like 2.9972 or something like that. I forget. You can look it up. But if you round to 3 times 10 to the 8th, that's fine. We typically give you for numerical questions about a 1 to 2% window of where we'll accept the correct answer. And that depends on how many steps the question is and stuff like that. So we kind of decide that depending on the nature of the question. But it's at least 1% leeway. And 2.997 versus 3 is like a much smaller difference than 1%. So rounding to 3 times 10 to the 8th is not going to cause any problems. So I've gotten the thumbs up from the questioner. So I think that means I've satisfactorily answered. But if anybody else has anything you want to clarify, please let me know. Okay, so that's perfectly fine to send questions in that way. We had a question in the chat that I was able to get to reasonably quickly, so feel free to do it in that format if you prefer. All right, so on to number 4 then. All right, so this is still chapter 2 material, and we have the element hafnium here. HF is the symbol. It's pretty far down the periodic table. It is observed that light with wavelength less than 318 nanometers is required to eject an electron from the surface via the photoelectric effect. What is the threshold energy work function for hafnium in joules? Now, it actually turns out that in this problem here, we're going to use the same equation that we just did, but it may not be obvious that that's the case. So first, let's talk about the concept that this problem deals with, because that is still relevant to this exam and still helpful to think about in this problem. So when we're talking about photoelectric effect, that's kind of an experiment where you have a metal surface. In this case, it's hafnium, but you can do it with any metal. So I'm indicating this is a metal surface. You shine light on the surface with some frequency nu and some energy h times nu. And when the product of h nu is greater than some minimum value, which we call the threshold energy or the work function, so if that, which is that's equal to the work function, or threshold energy is a synonym for that, both of those terms are given here. When that energy is high enough, you kick off electrons from the surface. And you can measure the kinetic energy of those electrons, and how fast they are relates also to the energy of the photon. But the key part is that if the energy of your photon is too small, then nothing will happen. You won't kick off any electrons. But if the energy is greater than the work function, then you'll start ejecting electrons. So here what we're looking for is we're actually giving you the threshold wavelength. So we can also just define that in terms of a wavelength, 318 nanometers. So that's our threshold wavelength, telling us that that's the maximum wavelength where an electron will be injected. We want to calculate what is the energy that's associated with that. So we're just going to use the same equation we did in the last problem, which is that the threshold energy is going to be related to the threshold wavelength by hc divided by lambda 0, where lambda 0 is the threshold wavelength. And you notice that they're inversely related to each other. So the photon has to have an energy that's larger than E0, which then means it has to have a corresponding wavelength that's smaller than lambda 0 because of that inverse relationship. So, but we're just going to use the equation to calculate the threshold energy or the work function E0, and we're just going to plug things in like we did before. So we have to do the same two constants, h and c. And again, I always do four 3 decimal places for h, but rounding to 3 times 10 to the 8th is fine for c. And then we have to put in lambda in the correct units of meters. So same story as last one. I'm not going to go through the conversion again in great detail, but it's 318 nanometers, which we have to divide by 10 to the 9th to get it into meters, which is 3.18 times 10 to the minus 7. All right, and so that's just going to be the same equation, and what we get is a value of 6.25 times 10 to the minus 19 joules. All right, and again, it's on that order of 10 to the minus 19. If it was positive like A or really negative like C, it's probably a mistake somewhere, but the one that matches would be choice D. And that would be the minimum energy then for ejecting an electron, which corresponds to the maximum wavelength of 318 nanometers. So it was set up a little bit differently, but it is the same equation, but it is still useful to review the concept of photoelectric effect because there could be conceptual questions related to that as well. All right, do we have any questions coming in? So far, no. So I will transition into number 5 then, keep us moving along. All right, so number 5 is we're dealing with the Bohr model now. So calculate the frequency of a photon needed to promote an electron from hydrogen's ground state into the third shell. Report the logarithm of your answer to 2 decimal places. I don't know if we have questions set up like this anymore. This is sort of old school format, but basically in some forms of the exam questions, which I don't know if they actually exist on the current test bank, but we would ask you to report the log just as a an easier way of reporting an answer that has a large or small exponential component to it. So don't get too bogged down in that. But if it asks you to do it, you have to learn how to take the log on your calculator. So make sure you know how to do that. But the important thing is to know how to actually do the problem. Okay, so for this problem here, anytime you see terminology dealing with hydrogen, promoting electrons, different shells, ground state, all that stuff, you should immediately zone in on the Bohr equation. And this is not given to you in the periodic table, this constant here, but this is the more, in my opinion, the more useful form of the equation. There is one that's a little bit different that some of you might be familiar with called Rydberg equation, but I always do this one because this one is useful in any situation. And then we're going to have that constant out front, and then it's going to be 1 over nf squared, where nf is the final value of n during the electronic excitation or relaxation, and then ni, both of those squared, where that's the initial value of n that it starts at. So that's what we're going to use first in these types of problems. So when you're doing a problem that deals with a Bohr model, you're typically going to start with this equation. Occasionally you'll have to work backwards in these, but the more common situation is the one like here, where you want to get the frequency of a photon associated with this event, promoting an electron from the ground state to the third shell, which is an absorption event. But we're going to typically start with this equation first and then work our way to what the question is asking for. So we're going to calculate delta E initially, and we need the two values of n to do that. All right, so the two values of n, the final value of n third shell, that tells us that nf equals 3. But then we didn't give you directly the value of the initial n value, but anytime you see ground state, hydrogen's ground state, that tells you that you're talking about n equals 1. So our initial value of n, where it starts, is n equals 1, which is the ground state. So those are the two n values we're going to put in. So 1 over 3 squared, 1 over 1 squared, the two values of n. And so what we get is a delta E, a change in energy for that electron of 1.94 times 10 to the minus 18 joules. And it makes sense that it's positive because we're going from a lower energy to a higher energy orbit or shell. But that's not where we want to stop here, because we don't want the delta E, we don't want the energy of the photon, we want the frequency of the photon that causes this to happen. So then for that, we have to recognize that the energy of the photon that would be involved in this is the absolute value of delta E, whether it's absorption or emission. So if you get the wrong sign for delta E, it's okay, as long as if you're just trying to find the energy or the wavelength or the frequency of the photon. But we get, and that's going to be equal then to h times nu, or hc over lambda. So once we do this first part of a Bohr model problem of calculating delta E using this equation, typically, or not always, but in a lot of cases after that, you're going to then use one of the equations for photon energy to be able to relate either that to whether that's either the frequency or the wavelength. And that's exactly what we're doing here. So we want to calculate frequency, so we're going to use h nu, and we're solving for nu, which is the frequency. So that's going to be the energy of the photon divided by h, which is Planck's constant. So the energy of the photon is the absolute value of delta E, so it's just that number. That's the energy of the photon that would cause the electron to be promoted between those two levels. So it's 1.94 times 10 to the minus 18 joules. And then we're going to divide that by h, which is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. And what we get is keeping at least one extra significant figure for now, times 10 to the 15th. 2.928 times 10 to the 15th hertz. In the current format of the exam, the most common way for you to have to enter that would be 2.928 E15. And the setup that I have here, which may show up in some of the questions, but I did not look through it closely to see if that's the case. So this would be one way to enter the answer, but here we're instructed to take the log. So if you're asked to do that, follow the directions, and you take the log of 2.928 times 10 to the 15th. So make sure you know the log function on your calculator in case that comes up, and it will later in the course, and that's 15.47. So pay close attention to answer format. I mean, if you miss a problem because of some stupid formatting thing, and it's obvious to me that you did it correctly, I can manually correct that when appropriate, but it's easier for you, easier for me, less stressful for all of us if you're able to just follow the directions the first time and put the answer in the format we're looking for. But anyway, whatever the answer format is, this is how you would approach the problem. And the key thing with Bohr model problems is to know what all the numbers mean that you calculate, and not to either stop too early or use the wrong equation in the second step. So it's often multiple steps, and knowing what to do with the numbers and knowing which steps are required for that particular problem is going to be key. So read the question closely, figure out what exactly it's looking for, and that's going to guide you to what you need to do. Okay, do we have any questions on that problem? Wow, we actually have a lot of people here today. It's like close to 40, I think. We usually get that many for the in-person reviews, so maybe I'm onto something, but I don't particularly like Teams. This is probably the only one we're going to do this way. All right, on to number 6. Still chapter 2. We're talking about electron configurations. All right, so number 6, which is from chapter 2. What is the ground state electron configuration for manganese? So this is going to be using the periodic table to figure out the correct number of electrons and also how they're arranged. So the first thing is, when we're doing problems like these, there will occasionally be times when we have to be able to connect the name of an element to its symbol. That is something that you're expected to be able to do for the first 36 elements on the periodic table. A lot of them are very common, but some of them not as much. Manganese is probably not the most common one, and people get it mixed up with magnesium. It's pretty similar. So manganese, which has the letter N in it first before G, is going to be Mn. So we have to recognize the symbol, because we have to find this on the periodic table. We actually saw this one earlier in the exam, although chances are it won't come up twice on your real exam. But anyways, manganese is Mn, and as we also saw earlier, I'm going to have to zoom out because we need to see more of the periodic table for this question. There we go. Okay, it's number 25. Already circled because we encountered it earlier. All right, but this question is dealing with the electron configuration. So when you have a multiple choice question dealing with electron configurations, which most of them are, the first thing to look at is, does the answer choice even have the right number of electrons in it? We can usually, or sometimes anyway, we can eliminate answer choices. So if manganese is atomic number 25, and it's not charged in this case, it's just manganese, then the correct answer needs to have 25 electrons in it. It turns out all of these do, so I didn't help you out on this particular one. But a lot of times, one or more of the answer choices will have the wrong number of electrons. So manganese is 25. The core electrons would be from argon in all of the given configurations. So that's 18 electrons there, plus whatever comes after that. So all 4 of these have 25 electrons in the configuration, 18 from argon plus 7 more that come after it. So we can't eliminate any of them on that basis alone. Sometimes one or more of the answer choices has completely the wrong number of electrons in it, so it's wrong no matter which subshells and things are populated. But we can't get rid of any of those answer choices here, so we actually have to go through and figure out then where, what the actual configuration is. So argon is the noble gas that comes before manganese on the periodic table. So when we're identifying configurations, we typically start with the noble gas that comes before the element. Mn is 25. The noble gas before that is argon, which is 18. So we're going to just write that in brackets. Now, after that, we get over to here, number 19. We're in the 4th row of the periodic table, 1, 2, 3, 4. So that's going to be the 4s block, 4s1, 4s2. And then this whole block of the periodic table, remember, is the D block. Sounds like something related to prison, but it's not. It's part of the periodic table. This is n-1d. So after 4s, we go to 3d, and then we're going to count over 1, 2, 3, 4, 5 to take us to manganese. So the last electrons we would put into the configuration for Mn are going to be 3d5. So the correct configuration would be argon as a core, 4s2 next, and then 3d5. And the only one that has that is choice A again. I guess I like choice A on this exam. But nonetheless, choice B has the wrong subshell, 4p. Choice C has 4d instead of 3d. Choice D has 3s instead of 4s. So it's only this one here that's correct and matches with choice A. All right, any questions on that problem or electron configurations?
I have a question.
Yes, absolutely.
Why is it not 4 instead of 3 since it's on a 4th row?
Because for the D block of the periodic table, it's n-1. The first row of the D block is actually 3D. So we're in the 4th row of the periodic table, but it goes from 4s to then 3D. So it's 3D, 4D, 5D. For the S and P blocks, it is exactly the row that you're in. So this is 1s, 2s, 3s, 4s, and so on. This is 2p, 3p, 4p. But for the middle part, it's going to be n minus 1. So it'll be 3d, 4d, 5d. And down here, even though we don't use those as much, that's going to be n minus 2. So this would be 4f and 5f. Okay. So it is a little bit different in those parts of the periodic table. That's just the order that those subshells come in. And you don't want to skip 3D. 3D is the first D subshell. And so that's why it's that part of the periodic table.
Okay, thank you.
Yep. Any other questions? All right, back to it. Number 7. All right, this question deals with the number of orbitals, the relationships involving quantum numbers. How many orbitals are there in the sublevel where n equals 5 and L equals 4? So for problems like this, you have to distinguish whether we're talking about a shell or a subshell, or a level or a sublevel, as they're sometimes called. And you need to distinguish, are we talking about number of orbitals or number of electrons? And just be very clear about what the question is asking. So here we're looking for how many orbitals, and we're telling you it's a sublevel. And even if we didn't tell you it was a sublevel, we're giving you an N and an L value. So when we give you both of those, N and L together, that defines a subshell. All right, so let's just go over all the different relationships then that are going to be related to problems like this. So if you're in a shell, or sometimes it's called a level, but usually a shell would only be defined by a value of N. And in that case, the number of orbitals is just equal to N squared. So in this problem, if we said how many orbitals are in the 5th shell, or in the shell where n equals 5, and that's all we give you, you would use n squared, 5 squared. But here we're giving you n and L, defining a subshell or a sublevel. So if we're defining a subshell or a sublevel, that's where we're giving you n and L together, or sometimes we just give you L but don't specify n. But if you have the value of L, you know that you're talking about a subshell of some type. In that case, the number of orbitals, which for some subshells you can get that from the periodic table also by counting how many columns there are, but in general it's given as 2L plus 1, which is what we'll want to use here. So that's going to be what we're going to use if we look for the number of orbitals in a subshell. So with n equals 5, there would be 25 orbitals, but then how many of those are in the L equals 4 sublevel? That's going to be using 2L plus 1. So to answer this question here, it's going to be that the number of orbitals is 2 times L, which is 4, plus 1. 2 times 4 plus 1 is 9. So that'd be choice D here. And again, it's because we gave you N and L together, or anytime you have L, that's the relationship you're going to want to use for the number of orbitals. Now, there is some related relationships that don't come up here, but just to make sure we're complete on covering them, in a given shell, the maximum number of electrons is now 2n squared, because there's up to 2 electrons per orbital. So n squared is number of orbitals, 2n squared is number of electrons possible. And then in a subshell, you just double the 2L plus 1 to figure out the maximum number of electrons. Again, this doesn't tell you how many electrons will be in that subshell. It tells you how many electrons can be. And it's 2 times 2L plus 1, because there's up to 2 electrons per orbital. So those relationships are helpful because we could also go through the exercise of figuring out all the different quantum number combinations, but that is usually more tedious and more prone to mistakes than just using these relatively simple relationships. But we have to remember them. We have to know when they're appropriate to use. All right, any questions on that problem or quantum numbers? Okay, on to number 8. So this is another one with a 2-part answer, not necessarily because you would have questions that are always 2 parts on the test, but just so I can review more of the concepts, I suppose. So anyway, in this question, what is the maximum number of electrons allowed in the n equals 5 shell, and how many of these can reside in the 5f subshell? So this sort of, uses the same relationship as the last one, but now we're talking about maximum number of electrons, not number of orbitals. so we're going to use the 2n squared for this one, because we're looking for first how many are in the n equals 5 shell. So in a shell, the number of electrons maximum is equal to 2n squared. And so that's going to be 2 times 5 squared, which is 50. So there's 50 electrons possible maximum in the 5th shell. And then how many of those are in the 5f subshell? Now, the other thing that this requires us to review is these letter designations for subshells. So we see this a lot where we don't use a number for L, we use a corresponding letter. So L can be 0, 1, 2, 3, 4, and so on. And those correspond to the letters S, P, D, F, and then pretty much alphabetical after that, although we typically only use those first 4. S, P, D, and F are the most common ones because those occur in real atoms. So here we're talking about a 5F subshell, so F tells us that L equals 3. And so that's the value of L we're going to use, where the number of electrons is 2 times 2L plus 1. That's the maximum number of electrons. Again, not how many there necessarily will be, but that's the maximum. L equals 3, so 2 times 3 plus 1 is 7. And then double that is 14. All right, so 50 electrons possible in n equals 5. 14 of those can go into 4F, and so that matches answer choice C here. And so that's, again, very similar to the relationships we used on the last problem. The difference is here we're talking about number of electrons, and because we can have up to 2 electrons per orbital, we double those expressions to get the number of electrons that are possible. All right, similar topics. So any questions on either of those?
So the 5 next to the F, we don't use that number, right, for any math?
Well, we used it in sort of the first part of the question because it was the first part dealt with how many were total in the n equals 5 shell, but for 5F, that 5 still represents the value of n. But when we're finding the number of electrons that are in the subshell, we don't need the value of n, we just need the value of L.
Okay.
All right, anything else? Okay. Moving on. This is Friday. All right, another quantum number question. So you're getting the idea, hopefully from this exam review, that quantum numbers figure prominently. I don't write the exams. I helped kind of put them together over the years, but I don't really write them myself. So whoever put this exam together was principally responsible, likes quantum numbers, because there are looks like 3 questions on that. So be ready. So this one asks for which of the following is a valid set of quantum numbers for a 4D orbital. All right, so here we have to, again, recognize now we're talking about 3 different quantum numbers, because an individual orbital also has a third quantum number associated with the m sub L. So let's quickly review the rules for quantum numbers in the relationship. So n can be any positive integer. Those are the possible values of n, the shell number. And then the values of L that you can have are related to that. They start at 0 and go up to n minus 1. So the biggest value of L is n minus 1. And then once you know the value of L, once that's specified, the possible values for m sub L go all the way from negative L to plus L, including 0 in increments of 1. So those are the possible values. We're going to introduce m sub L here, which we hadn't really dealt with before. So in this question here, we're talking about a 4D orbital. And as came up just on the clarification that was sought a little bit ago, when you have that as a designation for a subshell, which is a set of orbitals, or for a specific orbital in that subshell, as we do here, remember that the first number there is n. So in 4D, n equals 4. And then the value of L comes from the letter, which can be 0, 1, 2, or 3 for n equals 4. And we have letters that are S, P, D, and F. So we're talking about L equals 2. All right, so what we have is n equals 4 and L equals 2. And now we have to figure out, so that's going to be the first 2 numbers. So with that, we can eliminate choice C because it has the wrong L value, and choice E, which has the wrong L value. So both of those we can eliminate. because they have the wrong L value. But so we're looking for 4 and 2 is the first two. But now we have to figure out which of these remaining 3 answer choices has a valid third quantum number m sub L. So m sub L we have not talked about yet. It doesn't have as much physical significance, although it's related to the orientation of an orbital. But the key is that is minus L to plus L. So for an L equals 2 subshell, the allowed values of m sub L go from -2 to +2. So -2, -1, 0, 1, and 2 are all the possible values of m sub L. There'd be 5 orbitals, each with a different m sub L value. So these are the ones that are possible for m sub L. It has to be between -2 and +2. And so what we see is that choice B has 3, which is too big. Choice D has 1.5. Those values are never half integer values. They're always whole numbers. And so the only one that has a valid set would be choice A. N equals 4, L equals 2, which we specified from it being a 4D orbital. And then the values of m sub L can be anywhere between -2 and +2. So this one works out. That would designate one of those 4D orbitals out of the 5 that are in that subshell. All right. So do we have any questions then on that one, which also dealt with quantum numbers?
So for L, what do you mean that it can only go up to n-1?
So that's going to be sort of the limit of L. And so if you have, so here we're in the 4th shell, n equals 4, that's the number there. And that means the possible values for L in a n equals 4 shell would be 0, 1, 2, or 3. n-1, which is 3 in this case, is the biggest value of L that you can have. So that means in an n equals 4 shell, you would have 4s, 4p, 4d, and 4f subshells. In this case, we're specifying it as the 4d subshell, so that refers to L equals 2. So L equals 3 is possible, but because we're talking about a d subshell here, that's the value of L that we're specifying. So it's all the different possible values of L are bounded by n-1, starting at 0, bounded by n-1. So depending on what n is, so all these quantum numbers are related to each other in kind of this, top to bottom hierarchy where the value of n dictates which values of L are possible. The value of L dictates which possible values of m sub L you have. Hopefully that clarifies that a little bit.
Okay, one more question.
Sure.
So if we had 4 of F, it would be m sub L would be -3 to +3?
Yes, so if you had 4f, the only difference would be that you're specifying in that case an L value of 3. And with L equals 3, then the m sub L values now become -3 to +3. So it would also have more possible values of m sub L. And as we talked about in previous questions, that's because there are 2 L plus 1 orbitals. And so each orbital has a unique m sub L value. So the higher the value of L, the more m sub L values are possible as well. Okay, anything else?
What would it be if it were 4s, the 0?
4s would be L equals 0. So n equals still equal 4, because that's the number tells you. L equals 0 for s orbitals. And then when you have L equals 0, the only m sub L value is also 0. There's a single orbital in that subshell, and it has an m sub L equals 0. Plus L to minus L, well, there's no such thing as -0 or +0, which is 0. So that's the only value you can have for that one.
Okay, thank you.
Yep. Anything else? All right, doing okay on time, but we can still take more questions whenever they come up. On to number 10. All right, so this one asks for which of the following orbital diagrams reflects an atom in the ground state. So ground state means the lowest energy configuration for an atom, and we use the periodic table to predict where the electrons go, but this also then takes the additional step of looking at the relative spins of those electrons and which individual orbitals are occupied. Okay, so for these types of problems when we're dealing with the ground state of a multi-electron atom, there's 3 rules that we have to make sure are followed. So the first one, which is what the periodic table kind of allows us to follow, is called the Aufbau principle. That's where we fill lowest to highest subshells in terms of energies. And so if you go in the order of the periodic table, which starts at 1s and then goes 2s to 2p to 3s to 3p to 4s to 3d to 4p and so on. When you go in that order through the to the periodic table, that's allowing you to follow the Aufbau principle, filling the subshells from lowest to highest energy. And that's called Aufbau. Now, the other ones that are important are Pauli exclusion, which tells us that no two electrons have the same quantum numbers. Now, in terms of how that manifests itself in a diagram like this, it means that an orbital can have no more than 2 electrons in it, and when 2 electrons are in the same orbital, they need to be 1 spin up and 1 spin down. They have to have different m sub s quantum numbers for that to work. So that's the sort of manifestation of Pauli exclusion. And then the third one, which we have to consider in some of these as well, is Hund's rule, which is the one where you maximize the number of unpaired electrons. You singly, if you have degenerate orbitals in particular, you singly fill them first before you go through and start pairing up electrons. And that means you want as many unpaired electrons as possible. So we're going to have to think about all of these for this problem here. So if we go to choice A here, if it follows the Aufbau principle, because 1s is filled, 2s is filled, and then we have the last electrons in 2p. So that's the correct order, 1s, 2s, and then 2p. And then Pauli exclusion is followed. None of the orbitals have more than 2 electrons, so we're good there. But if you look at Hund's rule here, we see that our first electron is spin up, which means the second one should also be, or at the very least, they have to be the same. They have to either both be down or both be up to follow Hund's rule and to maximize this. So this one here we can eliminate because it violates Hund's rule. It does not maximize the number of unpaired electrons. It singly occupies the orbitals, which is correct, but it also you also have to arrange the spins to be the same as each other, being both up or both down when you do it like this. So this one violates Hund's rules because those 2 electrons are opposite spin. If we go to answer choice B here, what we notice is that we have an empty spot here in 2s. So we fill 1s, but then we don't completely fill 2s, but we're starting putting electrons in 2p already. So this one violates the Aufbau principle. You have to completely fill one subshell before you go through and put electrons into higher energy subshells. So we can't start putting electrons into 2p unless 2s is already filled. So this one violates that first one called the Aufbau principle. If we look at choice D here, sorry, C, we're not quite to D yet, we have Aufbau principle is followed, 1s filled, 2s filled, and then we start putting electrons in 2p. No violation of Pauli exclusion. We have 2 electrons at most per orbital, and when we do, they're opposite spins. And then we see that the 2 electrons, they're not next to each other. They don't have to be. They just have to be in 2 different orbitals, both with the same spin. So this is totally fine. Even though conventionally we put them right next to each other, they can be in any combination of 2 of those 3 orbitals with the same spin, and that still follows the rules. So this one follows all the rules, so we believe that that's going to be our answer choice here. Let's check that there's a problem with D. So D has the correct ordering of the subshells, 1s, then 2s, and then we start adding to 2p. But the problem here is that we put the second electron into the same orbital, which is another violation of Hund's rule. So none of these violated Pauli exclusion principle, but they either violated Aufbau principle or Hund's rule for the ones that don't work. All right, so we can eliminate A, B, and D by violating one of those rules. Choice C is the one that follows all of them. Okay, so those are taking just a little bit more detailed look at how the electrons arrange themselves in orbitals, which is related to electron configuration, but takes the additional steps of specifying the population of individual orbitals and whether the electrons have upspin or downspin. And so that's equals +1/2 or -1/2. Okay, any questions on that one?
I have a question.
Yep.
Would B be sorta an example? Because on one of the last homework it asked to show which one would be an excited state
Yeah.
using this. Would B sorta be an example if we said that one of those electrons moved from the 2s to the 2p?
Yes, B would be an excited state. We're not going to ask you a lot about excited states of multi-electron atoms, but yeah, if you take one electron from a ground state configuration and move it up to a higher energy subshell, that's how you would generate an excited state. So that's exactly what B is, because you can think of it as starting with C, which is correct, and then taking one electron and moving it over to the higher energy subshell and flipping the spin, but basically just taking one electron and promoting it. So that would be an excited state, not a ground state. So that is correct observation.
Thank you.
All right, anything else? All right, we've gotten to the top of the hill, so now let's do the second half of this review. All right, still dealing with periodic table. I can't remember if we've transitioned into chapter 3 or not, but we're close. I think we're not there yet. Chapter 2 is a lot of stuff. Yeah, we're still not quite in chapter 3 yet. But anyway, this one deals with predicting the charges of ions and the classifications of an element. So again, multiple concepts in the same question, mainly just for the purpose of making the review more useful. So which of the following show the correct classification and expected monoatomic ion charge for the given element? And so classification would be, things like metal, non-metal, halogen, main group metal, all those different terms we learned that sort of specify the place on the periodic table. And then monoatomic ion charge, that's where we predict the charge, also based on where it's located in the periodic table. So let's go through the 3 answer choices, and our multiple choice question has possibly more than one of those as being correct. So for number 1, which is potassium, we have to recognize that potassium is the atomic symbol K, one of the least obvious ones, but it is in those first 36. So now we have to find that on the periodic table and specify which classification it's in and what the charge of that would be if it formed an ion. So when we find K on the periodic table, it's number 19 over here on the left. And so the classification that's given in the answer choice is main group metal, and that would be valid classification for this one, because everything on the left side of the periodic table is a metal. Those in the first 2 columns in particular would be classified as main group metals, and they have more specific names as well. But in general, they're called main group metals when they're on the S or the P block. So, those 2 columns, first and second, as well as some of the metals that are, over here on the P block, like aluminum and gallium and lead and bismuth and things like that. Some of those are metalloids, but all those things that are in the P block that are metals are also called main group metals. So that's a fine classification. But then when we predict the ionic charge for potassium, it's going to want to lose enough electrons to get to the noble gas configuration. Since it's in the first column, it only has to lose 1 electron to achieve argon configuration. So we would expect potassium and everything else in the first column to form a +1 charge. But the answer choice was given to us as +2, so that one is incorrect. Because the charge is given wrong. So we don't want number 1 as part of our answer choices. But now we have to look at the next 2. So just write out that. So potassium is a main group metal. More specifically, it's an alkali metal, but that general classification is fine. But we would predict the charge to be +1, which was not correctly given in the answer choice. Number 2, which is aluminum, the symbol is Al. So this one is not the most obvious from its location on the periodic table, but we do want to be familiar with it. So Al is number 13 here. So the first thing, is it a a metal or a non-metal, or what is this classification? The staircase goes right here. And even though it's close to the staircase, it is to the left and it is classified as a metal. And I don't think that's surprising to anybody that's dealt with aluminum foil. It's a silvery, shiny, flexible substance, conducts electricity, all those properties we associate with metals, which we'll formalize more towards the end of the course, all associated with aluminum. So clearly aluminum is a metal, even though its position on the periodic table is kind of on the borderline. So it is a main group metal also because it's in the P block. Anything that's in the S or the P block that's a metal would be called main group. And then to predict the charge of aluminum, this one is not, again, the most obvious, but is one you're expected to know. The valence configuration for aluminum is 3s2, 3p1. And so if it's able to form a noble gas configuration, it does that by losing 3 electrons. It loses its 3p electron, both of the 3s electrons, and that gives it then the neon configuration. So aluminum is number 13. It's a metal, so it tends to lose electrons by losing 3 it gets to that noble gas. So the charge for an aluminum ion in an ionic compound would always be expected to be +3. So Al is also a main group metal, and that one doesn't really have a more specific classification than that, and it would expect to be a +3. So those are all given correctly in the answer choice. All right, and then finally for selenium, selenium is Se. And so when we find that in the periodic table, which is number 34, it's clearly to the right of the staircase, so it is a non-metal. It's not one of the metalloids. It's not right on the staircase. And then in terms of the charge of the ion, because it's a non-metal, we expect it to be more likely to form anions, which is what it does. So here it's in the 6A column, so it's 2 away from the noble gas. So it can gain 2 electrons to get to the Kr krypton configuration. So we would expect it to form a -2 anion if it was involved in ionic bonding. All right, so selenium is a nonmetal. And because it's non-metal, we expect it to form anions, and it's based on its column in the periodic table, -2 is the most likely anion that it would form. So that one is also stated correctly. So both 2 and 3 are correct, so E would be the answer choice we would choose. So that again relates to using the periodic table to make predictions about ions and also classifications. Both of those kind of came up in this. So do we have any questions on that?
Yes. So, would you only, okay, so whenever you're trying to get to a noble gas, you go to the left, so you take away electrons. So, when would you go to the right and or can you even add electrons or no?
Yeah, you can do either. So if you're if you're on the left of the periodic table, when we're dealing with metals, in that case you would go to the left, losing electrons to get to the nearest noble gas. You always want to get to the one that's closest, I suppose, is a way to think about it. So for these first 2 columns here, as well as for things like aluminum, you would lose electrons. That's what metals tend to do to get to the nearest noble gas. For things that are on the right side of the periodic table, they're close to the noble gas, but in the other direction, then you would add electrons. So you'd add 1 electron if you're in the halogen column here, group 7, to get to a -1 anion, or 2 electrons. I don't know if you can actually see my pointer on Teams, by the way. I forgot to mention that. That's one limitation of Microsoft Teams, is that, at least in the past, my laser pointer didn't work on Teams, my highlighter. So if you can't see that, I apologize. That's a limitation of doing it online that I can never figure out how to solve. But anyway, if you can kind of follow my gestation, you can see it or not?
Yeah, we can.
Oh, really? Okay, so maybe Teams improved, which is rare. All right, so yeah, for the nonmetals, these last 3 columns or so, when you're to the right of the staircase, the expectation is that they gain electrons and would form stable anions. They wouldn't lose electrons to form cations in that case.
What about the ones in the middle?
Those are hard to predict. So they behave like metals. So if you're talking about like the transition metals here, they behave like metals. So they tend to form cations and not anions. But there's no easy way to predict what the charges will be. They're usually variable. Most of these have more than one possible charge. You should be able to figure out what that charge is if we give you the formula of the compound, where you have the anion charge built into that. We might have problems like that later. But you can't predict it from the periodic table what the charge would be, and there's often more than one possibility. The only ones from the middle that you should probably know would be zinc is always +2, which again is not obvious from its location, but that's one that's pretty much invariant. And then silver this one's not as always, I suppose, but for our purposes is always +1. So those are not clear based on the location and probably not going to come up anyway. But the middle ones in general, you can't really predict what their charges would be. And there's usually more than one that's possible. All right, anything else related to that? All right, so the other thing that we can do with the periodic table is make predictions about certain properties, which we call periodic trends. And that's what this question deals with, really all of them: atomic radius, ionization energy, or electron affinity. And we're comparing oxygen and nitrogen to each other. All right, so we have 3 terms we're going to pair here: radius, ionization energy, and electron affinity. Now, in some level, these sort of work opposite of each other. So the directions that the radius decreases correspond to the directions in the periodic table where the other two increase. Although radius is a pretty smooth trend, ionization energy and electron affinity have some exceptions. All right, but if we look at radius first, that's usually the easier one because there's not really exceptions we have to worry about. What we have to recall is that as we go left to right in the same row of the periodic table, we're adding electrons to the same subshell. So we're adding electrons to subshells that are roughly the same distance from the nucleus to start with, but we're also adding more protons to the nucleus as we go left to right. And so that effect wins out, which means that as we go left to right across a single row of the periodic table, the radius will decrease. It gets smaller as we go left to right. So when we're comparing nitrogen and oxygen, we see that oxygen is to the right of nitrogen, so oxygen should be smaller. So in terms of radius, we'll do that one first and write it out so we don't forget it. Nitrogen should be bigger than oxygen because it's to the left. And for radius, there's not really any exceptions to that you have to worry about. Radius would then increase as we go top to bottom, because there we're adding subshells that are further and further away from the nucleus, but here we're comparing two that are next to each other left to right, so the one to the right would be the smaller one. Now, the next trend that this question asks about is ionization energy. For ionization energy and electron affinity, we do need to remember some exceptions to the trend. So let me sort of try to sketch those out as best as I can here. So for ionization energy first, as we go across the periodic table, the main groups of the periodic table, so 1 and 2, which are the first two columns, and then 3, 4, 5, 6, 7, 8, which are all in the P block on the right side of the periodic table. As we go across left to right, what we'll find is that they tend to increase left to right, but we have it sort of jumps up a lot here at group 2, and then comes back down in group 3, which will be kind of in between those two. And then it goes up at group 4. And then for ionization energy, we have a big jump at group 5. And then group 6 comes back down a little bit. And then it goes up to 7 and way up for 8. All right. But the important part is that it generally increases left to right, but you have exceptions here at group 2 and group 5, which for ionization energy are higher than you would expect. And that's because in group 2 and group 5, you have either an S2 or an S2P3 valence configuration, and those, for reasons that are hard to get into in a general chemistry class, but those are particularly stable. So you don't want to lose electrons if you already have S2 or if you have already P3. And so that makes the ionization energy, which is how much energy you need to pull off an electron, abnormally high for those two groups. So as it relates to this problem here, nitrogen is group 5 and oxygen is group 6. So based on this argument, we expect that even though the general trend is increasing left to right, as we go from group 5 to group 6, we see the decrease. That's where one of our exceptions occurs. And so for ionization energy, we expect nitrogen to be bigger than oxygen, even though it's to the left, but that's where that exception occurs. And then for electron affinity, we have the same exception, but it occurs in the opposite direction. So it's still generally increasing left to right for electron affinity over across the main groups of the periodic table. But here what we find is that for group 2 and group 5, electron affinity is abnormally low. So we have group 1, and then it's going to actually dip at group 2, and then go back up for group 3, up for group 4, dip at group 5, and then go up and up. And we don't really talk about electron affinities for group 8. They're essentially 0 as well. So again, it's not a smooth trend, but it does generally increase left to right. But at group 2 and group 5, we have the exceptions. And so that's again what we're talking about with nitrogen and oxygen is group 5s and group 6. And so this one, you don't have to necessarily remember the exception, but nitrogens would be abnormally low, and that would increase again as we go to the right to oxygen. So for electron affinity, nitrogen is smaller than oxygen. All right, so those are the three comparisons we made. So let's see which of these are correct. So the atomic radius of oxygen is larger. That's incorrect. The ionization energy of oxygen is larger. That is also incorrect. the electron affinity of oxygen is larger, that one is the one that would be true. And so the only one that works is choice C here, that the electron affinity of oxygen is larger than nitrogen. Okay, so those trends are going to come up from time to time, and ionization energy and electron affinity are just a little bit tricky because of the exceptions. If you remember that the exceptions occur at group 2 and group 5, and that they're going to be in opposite directions from each other, ionization energy abnormally high, electron affinity abnormally low in those columns, that should help you with any of these comparisons we ask you to do. So does anybody have any points of clarification on that one?
So we should remember the trends for the test, right?
Yes.
Okay.
It would always be qualitative, just comparisons, not really knowing exact numbers, obviously, but you do need to be familiar with the trends, and especially for ionization and electron affinity, where those small exceptions do occur.
Okay, thank you.
Okay. Ready for number 13? Okay, this is another ionization energy one, so this deals with the same concept. So now that we've discussed that, we can see if that again. Okay, so which atom has the largest ionization energy? We have a bunch of them chosen here. Nitrogen, oxygen, carbon, phosphorus, germanium. So not all of these are in the same row. So these three here are in the same row. They're all 2p elements. Then for phosphorus, it's a 3p element, and germanium, I think, is also a 3p. Let me make sure I remember that correctly. GE is over here, which is, sorry, even lower, 4p. So we have three different rows of the periodic table we're talking about. So in general, the ionization energy increases not only left to right, which we talked about in the last one, but also bottom to top. So as you go further and further to the top right, that's where the ionization energies get larger. So, germanium, phosphorus, nitrogen, oxygen, carbon, we would expect that these 2p elements, which are higher up on the periodic table and further to the right than most of the other choices, P and GE, should be the higher ones. So if we're looking for the largest ionization energy, we can, from these ones, eliminate germanium and phosphorus because they're so far down in the lower row and pretty far to the left, although the carbon's further to the left, but usually there's a pretty big increase as you go bottom to top. So it's going to be one of those three, carbon, nitrogen, and oxygen, that would be identified as the highest based on their location. And we again have to then think about the trend as we go left to right, which relates to exactly what we talked about in the last problem. So if you have carbon, nitrogen, and oxygen, which are groups 4, 5, and 6, remember that ionization energy is abnormally high for group 5. So it doesn't get so high that it completely blows out the rest of the ones near it, but it's going to be higher than group 6. So if I drew this accurately, you would expect that of these three elements, group 4 has the lowest ionization energy. Group 5 is then abnormally high, which makes it a little bit higher than group 6, which is kind of in between those two. All right, so that's going to be the trend that's relevant also to here, and that leaves us with nitrogen again is the highest one because of that spike we see in the group 5 elements. So similar to the last one, but this one also asks us to consider as well the trend of going to different rows of the periodic table, which was how we eliminated those other two answer choices. All right, any more questions on ionization energy or periodic trends? All right, so we are finally into the chapter 3 part of the test, which deals with bonding at a sort of a more basic level than we are going to cover in chapter 4 right now. And so the first question deals with the bond that has the smallest ionic character among the following. So for problems like this, we have to recognize the terminology, and this is one of the concepts that in dealing with student questions over the years seems to be one that is particularly challenging, and it requires a little bit of higher level thinking, because what we're dealing with here is when we say smallest ionic character, the first thing is the terminology. That means we're looking for the one that's least polar. So when we have bonds between two atoms, there's sort of two extremes and there's everything else in the middle. So if we have the same atom bonded to itself, like hydrogen bonded to hydrogen, this would be what we call a perfect covalent bond. The 2 electrons in that bond are shared exactly equally between the 2 hydrogen atoms, and that would be a nonpolar covalent. And then if we go to the other extreme, where it's a metal with a nonmetal, like sodium and chloride, we typically classify this bonding as ionic, where we don't share electrons anymore, but rather the nonmetal steals electrons from the metal, makes a cation and an anion that then are attracted ionically. And then everything else in the middle would be classified as a sort of polar covalent bond, so something like HCl. And so when you have this unequal sharing of electrons, either the extreme where it's ionic, or somewhere in the middle, which is a polar covalent bond, the sharing of those electrons is dictated by what's called the electronegativity of the atoms, another periodic property that we learned, which also increases as we go left to right and also as we go bottom to top. So same direction as ionization energy and electron affinity. But this time we're talking about the property of an atom when it's bonded to something else. And the nice thing about electronegativity is that the trend is very smooth. You don't have to really worry about exceptions like we did for the other ones. But the point is, if we move left to right or top to bottom or bottom to top, we increase electronegativity. And so in like HCl, you're going to have a partial negative charge on chlorine, a partial positive on hydrogen, because chlorine is more electronegative. And so what this means is that if you have higher ionic character, that correlates with a larger difference in electronegativity. So the same atom bonded to itself, the difference in electronegativity is 0, and that's when you have a perfectly covalent bond, or sometimes 2 different atoms have so similar in electronegativity values that they're basically nonpolar when they're bonded together. In the ionic extreme, you have a very large difference in electronegativity. Metals have very low electronegativity. Nonmetals have relatively high, and so that's a big difference. You get ionic bonding, and then polar covalent is somewhere in between, where there's a significant difference in electronegativity. Hydrogen is 2.1, and chlorine, I think, is 3. So there's a sizable difference in electronegativity, but it's not so big that you would classify it as ionic. So that's kind of the key concept of problems like this. When we say smallest ionic character, that means we're looking for least polar, which means we're looking for the smallest difference in electronegativity. Now, if I was being nice to you on this problem, what I would have done is given you one answer choice where it's the same atom bonded to itself. And if that was true, that would have to be the least polar, because that's completely nonpolar. Unfortunately, we don't have that as any of our options. We have 4 answer choices here, and all of them have two different atoms bonded together. So what we can do then is we can kind of compare them one at a time to each other, I guess in pairs to each other. So if we compare the first two, CO and CCl, when you're doing comparisons like this, it's helpful to pick 2 that have something in common. So we have, for the first 2, they both have carbon in them. So now we just have to figure out which is the bigger electronegativity difference, carbon-oxygen or carbon-chlorine. So in the periodic table, if you look where those are, oxygen is to the right of carbon, so it's definitely more electronegative, so that's going to be the more electronegative atom. And then chlorine is over here. We have to figure out which is more electronegative, oxygen or chlorine. And it's not obvious from the position on the periodic table because we're going down and to the right, which is sort of 2 opposing trends. So it's helpful to remember some benchmarks. And one benchmark is that fluorine is the most. The highest electronegativity is for fluorine. And then oxygen in terms of electronegativity is second most. So oxygen is going to be more electronegative than everything except for fluorine. So that means the difference between carbon and oxygen should be larger than the difference between carbon and chlorine. Because carbon is less electronegative than both, but oxygen has a bigger value, so that difference between C and O is bigger. And again, you don't necessarily want to memorize all the numbers, but carbon is 2.4. I've done these numbers enough that they're kind of stuck in my head now. Oxygen is 3.5 and chlorine is 3.0. So the difference between oxygen and carbon is bigger than the difference between carbon and chlorine. And remembering that oxygen is the second most electronegative element is helpful for some of these types of problems. Only fluorine is more electronegative. Okay, so that takes care. We're looking for the smallest ionic character, so we can eliminate CO because that would have a bigger ionic character than CCl, so it can't be the smallest overall. For the next comparison, we can look at CCl versus CF, and this one's actually a little bit easier comparison. And again, because both of these, chlorine and fluorine, are more electronegative than carbon, but fluorine is the most electronegative element. It's clearly more electronegative than chlorine because it's sitting right above it. And so that difference between C and F is going to be bigger than the difference between C and Cl. So for all the bonds involving carbon, carbon-fluorine would be the most polar covalent bond because fluorine is the most electronegative element. So that difference between C and F is the biggest you're going to be able to get among nonmetals involving carbon. So anyway, that tells us that this bond, CF, is more polar than CCl. We're looking for the least polar in this case. We can eliminate that one also. So then all that's left is to compare CCl and SiCl. And again, these are two bonds that share a common element, chlorine. So we just need to figure out what's the bigger difference, carbon versus chlorine, silicon versus chlorine. So we're looking for the ones that are further apart as we go bottom left to top right. And so what we notice is that both of these are to the left of chlorine, so they're least electronegative, but we go, silicon is below carbon. Number 14 here is below number 6, which is carbon. And because we're dropping down in the periodic table, silicon is less electronegative than carbon, meaning that the difference between silicon and chlorine is greater. Again, we're looking for the difference in the two values, not the absolute value here. And so silicon versus chlorine is a bigger difference than carbon versus chlorine. And so what that leaves us with is we would predict that this one is more polar, silicon chlorine, because of the bigger difference. So the one that came out smallest in all of these comparisons was CCl. And so that's going to be the one that we would pick as our answer choice. And again, if you're not going to necessarily have the numbers in front of you, but just to convince you that this is true, we said that carbon has electronegativity of 2.4, silicon is 1.8. So that difference between silicon and chlorine, a difference of 1.2, is bigger than the difference between carbon and chlorine. So when you're talking about bond polarity or ionic character, it's a little bit higher level of thinking because you can't just think about a single number. You have to think about the electronegativity for both elements and which one of those pairs has the biggest difference in their electronegativity values. And that's what's going to then relate to the polarity or the ionic character of that bond. All right, so any questions on bond polarity or electronegativity?
I have a question.
Yep, absolutely.
So, why is HCl an ionic bond but not a covalent? Because isn't H like +1 and Cl -1?
Well, so it is a polar covalent bond. Now, the reason for that is even though hydrogen's in a weird spot in the periodic table all the way on the left, it is still classified as a nonmetal. So hydrogen's in this column with a bunch of metals because it only has one valence electron, but in reality, it is a nonmetal. So whenever two nonmetals are bonded together, we would typically classify it as being a polar covalent bond rather than ionic. It does behave a little bit like an ionic compound when you dissolve it in water. And we're going to talk about that later in the semester. But for the purposes of classifying the bond, when you just have HCl, hydrogen chloride by itself, it would still be typically classified as covalent. Even though there's not a true distinction between ionic and covalent, typically if it's two nonmetals, we would always call it a polar covalent bond.
Oh, okay, that makes sense. So then if it's two, so an ionic bond will never be a metal and a metal or a nonmetal and a nonmetal, right?
That's correct. An ionic bond would be a metal with a nonmetal.
Okay, gotcha.
Metal-metal bonding is a totally different category that we would just talk about a little bit at the end of the course. But in terms of, yeah, ionic bonds is always one nonmetal with a metal.
All right, perfect. Thank you so much.
All right, anything else? Okay. Next question then also deals with radius, which we talked about earlier for atoms, but this one deals now with ionic radius as well. So we're comparing oxygen to chlorine and then O2 minus and Cl minus. And so again, comparisons are going to be useful by just doing two at a time, not trying to look at all four of them and pick it out right off the bat. So there's going to be, different combinations we can choose, but a pretty easy comparison would be to compare a neutral atom to an ion of the same element. So either a cation or an anion. And so if we go to oxygen versus O2 minus, the comparison is pretty straightforward because one's a neutral, one's an anion. And anytime you add electrons to something to make an anion, it's going to get much much bigger. And that's because you increase electron-electron repulsion, putting these two extra electrons into the same subshell. But now you have more electrons, crammed into the same volume of space. They repel each other strongly, and then they want to spread out, and that makes the whole thing bigger. So between oxygen and oxygen 2-, the anion, we expect O2- to be much bigger. So that's a general thing you can easily remember, is that anions are much larger than neutral atoms. I'm going to put a underline on much because it is a pretty big effect. Just adding 1 or 2 electrons really blows up the radius in a pretty big way. So again, you don't have to remember numbers or know the numbers, but it's significant, very significant. All right, so that makes that we're looking for the largest one here. So O2- is clearly larger than oxygen, so we can get rid of that one. And then similarly, when we compare, Cl and Cl-, what we have is, again, an atom and an anion. So even adding 1 electron, as we did here, is enough to really increase the radius. It will always increase the radius when you add electrons. Conversely, it will decrease the radius if you take them away, but we're only dealing with anions in this problem. So again, Cl- much bigger than Cl by the same argument. So we're looking for the biggest ones. We can get rid of the 2 neutrals, but now we have to compare 2 anions to each other, Cl- and O2-. And when we're comparing anions to each other, or anions and cations, we can't just focus on the periodic table only, because we've added more electrons, or with cations we've taken some away. So we do need to think about where those valence electrons are, because it may not always be indicated from the periodic table, because for ions, again, you're changing the number of electrons. So if we have Cl- versus O2-, we can think about, where do those electrons reside? Where are the valence electrons in both of those? So Cl here is number 17. It's in the 3p block of the periodic table, 3rd row, p block. And when we go to Cl-, we're just adding 1 more electron to the 3p to get to argon configuration. But the point is, the valence electrons in Cl- are in the 3p subshell. Versus oxygen, we're up here in 2p. So oxygen is 2p4. And then we add 2 more electrons also to the 2p. So the valence electrons in the oxide anion would be in the 2p. So when you're comparing charged species, you also want to think about where those electrons are. So for Cl-, they're in the 3p subshell, the outermost electrons. For oxygen, they're 2p. And as you get to higher principal quantum numbers, n equals 2 versus n equals 3, or as you go higher and higher, that tends to lead to larger and larger radius. So we would expect the 3p valence electrons for chloride to be further away from the nucleus than the 2p electrons for oxide. So we would predict that Cl- is bigger. Even though the charges are different, if you go to a whole different subshell further away from the nucleus, you expect that to expand the radius, and so we would expect Cl- D to be the biggest overall. So that other part of this comparison is that when you're comparing 2 anions, or I guess I could just say ions in general, whether it's cations or anions, if they're in the same row of the periodic table, look for the one that has the higher charge. The more positive charge you have, the smaller it is, the more negative charge you have, the bigger it is. But if they're in different rows like we had here, the lower you go in the periodic table, the higher the period number, the higher the row number, that's going to be the bigger that you get. So that was a relevant one for this one, because we're talking about 2 ions that are in different rows of the periodic table. So the one that's further down in the 3p, we expect to be bigger than the one that's in 2p. If they were in the same row, then the one that has the larger charge, or we would base it on charge. The more negative charge, the bigger. The more positive charge, the smaller. But in different rows, we have to think about which subshell would be further or closer to the nucleus. All right, any questions on that? Okay. So then the last few questions deal with different aspects of ionic and covalent compounds, either predicting formulas, naming them, and so on. So here we have predict the formula of the compound that forms when calcium and chlorine react. So for problems like this, we've already talked a little bit about predicting the ions that would form from an element, positive ions for metals, getting to the noble gas configuration, negative ions for nonmetals to get to the nearest noble gas configuration that's to the right of it. So that's going to be the first step in a problem like this. If we want to predict the formula of an ionic compound, and this would be ionic because calcium's a metal, and over here, number 20, chlorine is a nonmetal over here, number 17. And so it's a metal with a nonmetal, so it's ionic. So the first thing we have to do is predict the charges of each of those. So calcium is number 20, and it's in group 2A here. So all of the elements in this second column periodic table we would predict would form a +2 cation. It loses 2 electrons to get to the nearest noble gas configuration. So that's going to be +2. And then chlorine, which is over here in number 17 in the group 7A, all of the elements in this column would gain 1 electron to form a negatively charged anion, a -1 anion, to get to the noble gas configuration, in this case also argon. So that's how we would predict their charges based on the location of the periodic table. The metal forms a cation, the nonmetal forms an anion. So calcium being in group 2A, we predict would have a +2 charge when it forms an ionic compound. And then chlorine, which is in group 7A, on the far right of the periodic table, we would predict has a -1 charge when it forms an ionic compound, forms an anion. So those are the two charges, and then from there we just have to balance them to get the correct formula. We have to make sure that the positive and the negative charges cancel each other out. So we have calcium 2+ and Cl-, and again, the sort of low thought way of doing this is just to take the charges and cross them over to make them as subscripts, but either way we just have to make sure that we have the same number of negative charges and positive charges. So what we need then is 1 calcium 2+ paired with 2 Cl- to balance the +2 charge from the metal with 2 -1 charges from the nonmetal. So CaCl2 is the correct formula for this compound, which is called calcium chloride, and that would be answer choice A given here. All right, any questions on predicting ions or ionic formulas? All right, very good. Just 4 more to go. These exam reviews always take a while, but hopefully they're useful for you guys. All right, number 17. In the Lewis structure for carbon monoxide, what is the formal charge on the oxygen atom? All right, so when we're doing these, we have to first get the formula of the compound to be able to draw it. So carbon monoxide is a covalent compound, so we use prefixes to indicate. No prefix on the first element means there's one of them. Mono means one as well, so it's just CO is the formula for carbon monoxide. So a deceptively simple Lewis structure, just 2 atoms involved, but we still have to make sure that we count the electrons correctly and that we follow the octet rule and all those things. Okay, so let's count the electrons first for carbon and oxygen. Valence electrons that we care about for Lewis structures. All right, so when we go to the periodic table, in these main group elements, the group number directly tells you the number of valence electrons. So carbon is in group 4, meaning it has 4 valence electrons. Oxygen is in group 6, so it would have 6 valence electrons. So 4 from carbon, 6 from oxygen for a total of 10. 1 carbon in the formula. One oxygen in the formula, and a total of 10 electrons then when we add those up. Okay, so then the next thing we have to do is draw the Lewis structure. This is only 2 atoms, so again, it seems like it should be easy, but we have to make sure we complete the octet rules. So if we follow the same approach that we usually do, it's kind of arbitrary which one you call the central atom because there's only 2 of them. But we start with a single bond between them, and then we're going to complete the octet on one of the 2. It doesn't really matter which one you complete the octet on first, although conventionally we would complete the octet of the more electronegative atom first, which is oxygen. But either way, you're going to complete the octets of one of them. So we've completed the octet on oxygen. That gives us 10, or sorry, that's 8 electrons, but we have 10 total, so that leaves a lone pair on the other one. Again, whichever order you did that in, whether you completed the octet on carbon first or oxygen first, you would end up with 1 lone pair on the other one. But this is clearly not the finished structure because one of the 2 atoms, in this case carbon as I've drawn it, only has 4 valence electrons around it. it has 2 electrons in this bond here, 2 more from a lone pair, but that's only 4. And everything that's in the 2p block of the periodic table, starting with carbon, oxygen, nitrogen, fluorine, would always want to have 8 valence electrons in a stable Lewis structure. So this only has 4, it needs 8. We can't just add more electrons because we've used all 10. So the way that we do that is with multiple bonding. So we need 4 more electrons around carbon, so we need to draw 2 more bonds to it with 2 electrons each. So we're going to take 2 lone pairs from oxygen and turn them into multiple bonds, making a total of a triple bond. The 1 bond we already had plus the 2 new ones to complete the octet. So what that leaves us with is a structure like this, where we have a triple bond between the 2 atoms and 1 lone pair on each one. And if we check ourselves, what we have is a total of 10 electrons, 2, 4, 6, 8, 10. 2 lone pairs, 6 more in the bond, is a total of 10. And we completed the octet on both atoms. 6 from the bonds for each of them, 2 more from each lone pair. So that's a total of 8 for each atom. So this follows the octet rule, has the correct number of electrons. And then finally, what this asks us to do is calculate the formal charge on the oxygen atom. So we can calculate the formal charge on both of them just to practice, but we need oxygen for this one. So carbon and oxygen, the way that we calculate formal charge for carbon is we take the number of valence electrons, which was 4 for the atom. We subtract the number of bonds, which is 3, it has a triple bond. And then we subtract the number of non-bonding electrons, or the total number of lone pair electrons, which is 2, 1 pair. So 4 minus 3 minus 2 is minus 1. So this has a minus 1 formal charge. And then for oxygen, it's in group 6. So 6 is the number of valence electrons. It also has 3 bonds, same triple bond that it shares with carbon. Also has 2 non-bonding electrons. So 6 minus 3 minus 2 is plus 1. My tablet is starting to lag just as we get to the end, so hopefully we can make it. All right, so we have a -1 and a +1. The one for oxygen is +1, so that would be the answer in this question, +1. And this is, again, a weird Lewis structure, even though it's deceptively simple with only 2 atoms, because it's a neutral molecule, but you still have a plus and negative formal charge. And moreover, the positive formal charge is on the more electronegative atom, which is especially weird. But there's no other way to do it if you want to follow the octet rule. And the octet rule is the most important. So this is the only way to draw the Lewis structure of carbon monoxide that gets all of that correct. Follows the octet rule, has the right number of electrons, and so on. All right, so any questions on that one or Lewis structures in general? Are we still recording? Good. I saw a message pop up about recording and I panicked that it had stopped for some reason. All right, so we'll go on to the last 3. So the next one deals with nomenclature, naming compounds. These ones are ionic compounds in particular. So it wants to know which of the following name formula pairs is incorrect. So we have strontium carbonate, cobalt-2 nitride, calcium phosphate, zinc sulfide, and potassium chlorite. Did I screw this up and make all of them correct? No. Okay, good. I thought I made a mistake. All right, so the first one is strontium carbonate, SrCO3. So if we go to the periodic table, again, we have to figure out the charges of the ions and make sure that they're balanced and all that stuff. So Sr is the metal in the formula. It's not one you'd have to know off the top of your head, but here you have enough context to find it because the symbol is given in the answer choice. And so Sr is in group 2, so it would form a +2 cation. And then what we have to remember, sort of, I guess by memorization more than anything, is that carbonate, which is CO3, this is really starting to drag. I hope we can get through this. Let me save this so I don't lose it. That's why I hate Teams. It doesn't, eventually it will slow down your tablet. Oh, maybe it's because I'm not plugged in. Maybe I'm running low on battery. Give me a second. I thought I had this plugged in. All right, let's see if that changes it. All right, so anyways, strontium +2, there we go, is running out of battery and didn't decide not to warn me, just slowed down. And then we have CO3, which is carbonate. And we have to remember from our list of polyatomic anions that carbonate is 2-. All right, and so for this one, +2 cation, minus 2 anion, so one of each in the formula would be correct. All right, it would balance the charge with just one of each. So that one is correct. If we go to cobalt-2 nitride, CO2N, so to figure out if this is the right formula, we need to again think about the charges of each ion. In transition metal compounds, the charge is given in parentheses with Roman numerals. So cobalt-2, cobalt is a transition metal right there, means it's a +2 charge on the metal. And then nitride, nitrogen is here in group 5. It would want to gain 3 electrons to get to a noble gas. And so what that means is that we expect nitrogen to have a -3 charge as an anion. So the two ions involved are cobalt-2 plus, that's directly given to us in the name, and then N3 minus, which we predicted from the periodic table. So if we cross these over and make them into subscripts to get the formula, the correct formula for this should be cobalt-3N2, not cobalt-2N. So this is the wrong formula here, or the wrong name for that formula. This formula would be, I guess, cobalt 1.5 nitride, which is a weird name. But anyway, the name or the formula is wrong, but because from cobalt-2 nitride, we would predict a formula of CO3N2 to balance the charge from the +2 cation and the -3 anion. That gives us +6 and -6. So that's the wrong formula, so that should be the one that we would pick as our answer choice. Let's verify that the rest of these are correct. Calcium, as we saw earlier, so I'm not going to flip back to the periodic table, was Ca2 plus. And then phosphate, we have to remember, is PO4 3 minus. So that's the formula and the charge for the cation and the anion. And so when we make that into a formula, what it comes out to is Ca3 and then 2 phosphates, PO4 taken twice. So that one is correct. Zinc sulfide. We talked about this one earlier, that zinc is always +2, even though it's not obvious in the periodic table. It's in the transition metals, so you might think that is variable, but zinc, we should remember, is always +2, even though it's a transition metal. So zinc +2, and then, sorry, I should go back to the periodic table. Sulfur here is in the 6th column, group 6A, so 2 minus to get to the noble gas. So we have 2 minus anion with a 2 plus cation. So we just need one of each to make zinc sulfide. It wouldn't probably be wrong to say zinc 2 sulfide. Anytime you're dealing with transition metals, if you want to put the Roman numerals in parentheses, it's okay. So it wouldn't be wrong to say zinc 2 sulfide. We don't necessarily need to specify it here because zinc is always +2. But either way, that one's correct. And then finally, potassium chlorite. K is K plus. It's the first column of the periodic table. Chlorite, we have to remember, is ClO2 minus. All of these oxoanions of chlorine, hypochlorite, chlorite, chlorate, and perchlorate, they have different numbers of oxygen atoms, but they're all -1. But anyway, +1, -1 means we just need one of each. So KClO2 is the correct formula. So the only one that had a mistake was choice B, which is what we were looking for, the one that's incorrect. All right, do we have any questions on naming ionic compounds? Okay, just 2 more to get through. The next one is covalent, which in some levels is a little bit more straightforward, except for the acids are a little bit. I only have 3 answer choices. Oh, okay, so this is just one we're just giving the formula. Again, you'd only have to do 1 on an exam question, most likely, but we're just doing 3 to give you 3 examples of how we name these things. All right, so the first one here is dichlorine heptoxide. So for binary covalent compounds, 2 nonmetal elements in the formula, chlorine and oxygen, going from name to formula is very straightforward as long as you remember the prefixes. So the names have these prefixes in them that directly tell you the number of each atom in the formula. So dichlorine, that's going to be Cl2, and then hepta means 7. You leave out the A when it's with oxygen, but still hept means 7, so Cl2O7 would be the formula of this compound. So going name to formula or vice versa for binary covalence is usually pretty easy to do as long as you remember which prefixes correspond with which numbers. The next 2 are acids, which are a little bit more tricky to find the formulas of. Now the key with acids though is you need to figure out which anion is involved in forming that acid, and that comes from the first part of the name. And then once you have the charge in the formula anion, you just pair it with enough hydrogens to balance out that charge, 1+ charge for each hydrogen. Okay, so we have hydrocyanic acid. Cyanide this comes from the cyanide anion, which we have to remember is Cn-. So cyanic comes from cyanide as the anion. The formula for cyanide is Cn-. It's one of the polyatomic ions on the list that you have to know. And so if we want to make an acid out of this, we have a -1 charge, so we need to add 1 hydrogen to the formula to balance that -1 charge. So it becomes HCN. All right, so anytime you make an acid, you have to figure out the charge of the anion, either based on its location in the periodic table, or if it's polyatomic, based on what the charge for that anion is that you have to remember. And then you balance that charge with enough hydrogen atoms to do that. So HCN will be this one. The reason is hydrocyanic acid, we use hydro anytime it's not an oxoanion. So this ion is polyatomic, but it doesn't have oxygen in it. So anytime it doesn't have oxygen in it, we still give it the hydro prefix that we would use for other types of acids also. So that's hydrocyanic acid, HCN. And then chloric acid, well, we have to remember for acids that have ic in the name, or OUS is the other one, if it's an ic acid, it comes from an 8 anion. And if it's an acid that has OUS, so if it was chlorus instead, that comes from an ITE anion. So ic corresponds with 8 from the anion, OUS corresponds with ite from the anion. So because this is chloric acid, that tells us that it comes from the chlorate anion, because IC changes to ATE in acid names. And so chlorate, we have to then remember, again, more polyatomic ions, definitely make sure you're up to speed on those, is ClO3-. That's the chlorate anion formula. And once again, anytime we're forming an acid, we just need enough H+ hydrogen to balance the charge. Well, there's only a 1 negative charge, so this one also just needs 1 hydrogen in the formula to make it HClO3. Okay, so for naming acids, it's probably the most complicated naming that we had, to be honest. And it does require you to know the names and charges of the ions, the anions as well, that are then used to form that acid. All right, any questions on nomenclature of covalent compounds, either binary compounds or acids? All right, very last question then on this review is another one dealing with Lewis structures. In this one, we're going to specify that we want to draw the Lewis structure of this compound here that minimizes formal charges. And we want to know how many double bonds are there and how many lone pairs are on the central selenium atom, respectively. So again, in ambiguous formulas like this, we'll often specify the central atom. So if you read the question all the way through, you'll see that Se should be at the center. And then what we're going to do is we're going to draw the Lewis structure, we're going to minimize the formal charge, and then we're going to figure out how to answer the questions, how many double bonds and how many lone pairs are there. Okay, so let's count the electrons first. We have chlorine, selenium, and oxygen in the formula. So we're going to go to the periodic table and locate those elements and figure out how many valence electrons they each have. Chlorine is group 7, so there's going to be 7 valence electrons from each chlorine. Selenium is group 6, so there's going to be 6 from that one. Oxygen is also group 6, so 6 more from oxygen. So 6, 6, and 7 are the valence electron counts for those 3 elements. There's 2 chlorines in the formula, each with 7 electrons to our valence count. Selenium, there's 1 in the formula, and it contributes 6. And oxygen, there's 1 also contributing 6. All right, so 14 plus 6 plus 6 is 26 valence electrons. All right, so that's going to be the number of valence electrons that we want to include in this Lewis structure on the way to minimizing the formal charge. And so we'll start with our central atom, single bonds to each of the outer atoms in whatever arrangement we put them in. And we'll complete the octets on the outer atoms first, just like we always do. So 6 more electrons go onto each outer atom to give them a total of 8, 2 from the bond plus the 6 more that we've just added. And what we've done now is we've completed 3 octets all three outer atoms have a complete octet. So 3 times 8 is 24. The total number that we have available is 26, and so we need to have 2 more electrons on the central atom as lone pair. All right, so if we were asking you to draw the Lewis structure that follows the octet rule, this is where we would stop, because we have exactly 8 electrons around each atom. 8 from the outer atoms, which we took care of by adding all the lone pairs, and then by putting this lone pair on the central atom, that also has exactly 8. But what we're asked to do in this problem here is to minimize formal charges. And so when we calculate formal charges in this compound, for the 3 atoms in the formula, for chlorine, it's in group 7, so it has 7 valence electrons. It has 1 bond, and each chlorine has 6 non-bonding electrons around it. The 2 chlorines are identical, so their formal charges both come out to 0. Typically, if you have outer atom halogen atoms, you're going to get a single bond, and that's it. So those ones are fine, but then if we go to selenium and oxygen, as it's drawn right now, so selenium is a group 6 element, it has 1 bond, or sorry, 3 bonds, 1, 2, 3, 1 to each outer atom, and it has the 2 non-bonding electrons on it. So 6 minus 3 minus 2 is plus 1. And then for oxygen, which is also group 6, it has 1 bond, just a single bond to the central atom. And it has 6 non-bonding electrons around it. So that's minus 1. So in this structure that we've drawn, which follows the octet rule, we have a plus 1 and a minus 1 formal charge right next to each other. And we're asking you to minimize formal charges here. So to do that, we have to expand the octet of selenium, but we can because it's in the 4th row of the periodic table way down there. So if we have a plus 1 and a minus 1 next to each other, the way that we get rid of that is we take off a lone pair and make it into a double bond. So we're going to remove one of the lone pairs from oxygen, turn it into a double bond between the 2. And now when we calculate formal charges, I'm just going to erase what I did and recalculate them here so I don't take up more space. For selenium, it now has 2 bonds because it now has 4 bonds because then you have the double bond plus the 2 single bonds, and it still has its 2 non-bonding electrons. So that comes out to 0. And then this oxygen has now a double bond, 2 bonds, and then the 4 non-bonding electrons that it's left with also comes out to 0. So this structure here, which has a selenium-oxygen double bond, is the one that minimizes formal charge. Now every single atom in this structure has 0 formal charge, which is ideally where you'd like to get to for a neutral atom or neutral molecule if we're asking you to minimize formal charge. So that's the one that has, and so we have how many double bonds? We have 1 double bond. And then how many lone pairs on the central atom? Well, whether we minimize formal charges or not, we have that 1 lone pair. So there's 1 of each, one double bond and 1 lone pair on the central atom. So choice B is the correct one here. So for problems like this, you need to be able to draw Lewis structures very well, both for this exam and for the next one, as it turns out, for the stuff we're doing in chapter 4. And for Lewis structure questions, you have to make sure you read the question closely. And if it matters whether octet rule or formal charges should be considered, we'll typically specify that as we did here. All right, so that takes us to the end of the 20 questions. So any questions on that one or anything else that you think might come up on the first exam that you want me to cover before I adjourn this meeting? All right. Yep, go for it.
I was having a little trouble on the homework questions where they ask you how many unpaired electrons a particular atom has,
Okay.
especially in the transition metals.
Yeah. So for those ones, it's going to be kind of related to, we didn't do an exact question like that, but it's related to this concept here of following Hund's rule that we talked about way up here in number, what was it? 9 or 10, number 10 here. So you want to sort of consider diagrams like this. So if we give you a transition metal, let's say we do iron, and we want to know how many unpaired electrons there are. So the starting point for that is going to be the electron configuration. So for iron, it's going to be argon, 4s2, 3d6. Let me see if I got that right, but that's right for iron. If I didn't get that right, I have to turn in my inorganic chemistry card. So argon is the core, and then we have 4s2, 3d, 1, 2, 3, 4, 5, 6. So for questions that deal with unpaired electrons, you have to write the configuration out first. Now, in terms of then what you do from there, you only need to consider subshells that are partially filled to identify how many unpaired electrons there are. Anything that's completely filled, all the electrons have to be paired to be able to follow the Pauli exclusion principle. So all the argon core electrons will be paired. And then 4s2, that's a completely filled subshell. So you could draw it out, but it's going to be 2 paired electrons. But then when we get to 3d6, that's where there could be unpaired electrons that we have to figure out how many there are. So in the 3d subshell, again, either using the periodic table or using relationships we learned earlier, L equals 2 for 3d, so 2L plus 1 equals 5 orbitals. Or alternatively, we know that on the periodic table, the 3D part of the periodic table is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements wide, meaning that there's up to 10 electrons or 5 orbitals present. So you have to know that there's 5 orbitals in a 3D subshell. And now we just have to follow Hund's rule to be able to populate these with the 6 electrons that are in there. So it's going to go 1, 2, 3, 4, 5. We individually fill first, and then we have to pair one up in 6. So these 2 are paired, but the other 4 would all be unpaired in this case. So this would have 4 unpaired electrons in the ground state when you follow Hund's rule and do it in that way. So that's anytime you're dealing with number of unpaired electrons, that's kind of the level of analysis you want to get to. For transition metals, the key is that there's going to be, a set of 5 d orbitals in the valence, and you need to fill those with the correct number of electrons one at a time first before you pair them up.
Thank you.
All right. Okay, good. Anything else related to exam 1? All right. I will have my normal availability on Tuesday for, in-person office hours, and I'll probably be there for a lot of the afternoon as well. So, if you need to stop by after the regular hours, there's a good chance I'll be there. You can clarify with me on other times. And you're welcome to send me questions via email or any other form of communication that you can find me at. So good luck on the first exam, and I encourage you to do the practice exam in Blackboard. That should have, I'm not sure if it's open up yet, but it'll be open up by tonight if it's not already. And I will see you guys next week, either in class or outside of class, if you have any last questions. Okay, so thank you all for coming, and those of you that are watching the recording, same to you, and I'll see you guys in a little bit.